In this video, we are going to show that if a, m, and n are positive integers such that m is greater than n, then a raised to the power of 2 to the n plus 1 divides a raised to the power of 2 to the m minus 1. So the first thing we are going to do is to let a, m, and n be positive integers such that m is greater than m. Now, since m is greater than n and m and n are positive integer, what do we have? So we gotta have m minus n is a positive integers. So once m minus m is a positive integer, so there exists positive integer k such that m minus n equal k. That means that we can have m equal to n plus k. Okay, then what next? So try to write this term right here, a raised to the power of 2 to the m. So we gotta have a to the 2 to the m minus 1 becomes a to the 2. Now m becomes n plus k minus 1. Then we're gonna have a raised to the power of 2n 2k minus 1. Then we have a to the 2n and raised to the power of 2k, just the property of index. And then we are going to have a raised to the power of 2n raised to the power of 2 to the k minus 1 raised to the power of 2 to the k. And then what we are going to do? Right now we have this number raised to the power of 2 to the power of k, and 1 raised to the power of 2 to the power of k, and 2 to the power of k is an even number. So we are going to use this. We are going to use the difference of two even powers. So we let p to be positive integer n. For all real numbers x and y, we're gonna have x raised to the 2p minus y to the 2p. So we can write x minus y times x plus y times the sum from I equal to 0 to p minus 1, and the term and the sum mean. The sum mean is x raised to the 2 times p minus I minus 1 and y raised to the 2i. This is the formula that we have to use. And this formula is derived from difference of let's say n power. Okay? It's like x to the n minus y to the n. And it has its own formulas. Okay, so let's continue. So we use this formula to apply with this. Okay, so what do we have? We start with 2. Okay, we have a to the 2m minus 1 equal what? A to the 2n raised to the power of 2 to the k minus 1 to the 2 to the k. Okay, what next? So we're gonna have a to the 2n minus 1. So we are trying to apply this formula. It's like x is a to the 2 to the n, and y is 1, times a to the 2n plus 1. So this is the term we want to have. This one right here. And this summation. So we're going to have summation from I equal to 1 to k minus 1. And the first term is a, right? So we're going to have a to the 2k minus I minus 1, 1 to the 2i. Okay, so 1 to the 2i becomes just 1. So we're going to have, okay, we're going to write like this. A to the 2 to the n plus 1 times a to the 2n minus 1 times summation of, okay, we start from I must start from 0, not 1. Okay, start from 0 to the k minus 1 and a to the 2 times k minus 1 minus I. That's it. Okay, and this term right here is just 1. So now we have this product multiplying the summation of a, where a is a positive integer raised to the power of 2 times integers. Okay, so this number is actually is a positive integer, and this number is also positive integer. Okay, so what do we have? So since this term, this number, oops, what happened here? Since this number is integer, okay, is an integer, and we have a to the 2 to the m minus 1 equal this term right here. Okay, then what do we have? And we have this is our divisor, a to the 2 to the n plus 1, and this is our quotient. So that means that we can conclude that a to the 2 to the n plus 1 divide a to the 2 to the m minus 1. That's it for this proof. So we have shown that if a, m, and n are positive integers such that m greater than n, then a to the 2 to the n plus 1 divides a to the 2 to the m minus 1. So that's it for this video.